Okay, in this video, we continue our discussion of basic Bayesian statistics. In particular, we consider point estimation of one parameter. We are still using the same reference book, Empirical Bayes Methods, second edition. This video consider example 1.3.1. In this example, we have conditional density and the prior density are both normal densities. In this video, I do a few simple things. First, I try to derive the posterior density and the marginal density, and then try to derive the simple decision of point estimation, and then also we try to evaluate the base width. Here in the first page of the notes, I explicitly write down the normal density. So here f x conditional on lambda. The mean is lambda and the standard deviation is sigma. And in the prior density, the mean is mu g and the standard deviation is sigma g. Okay, and because we need to calculate the marginal density and the posterior density, we need to evaluate this quantity f multiplied by g. And but the most important thing is how to evaluate the argument in this exponential function, which I here denote it by star, red in color here. And the skill that we keep using in this video is computing square. Okay, and essentially the reason is that in normal distribution there are only two parameters. So in fact we do not need to calculate the marginal density and the posterior density explicitly. We just need to do enough algebraic manipulation so that we can observe what will be the mean and variance. Okay, to be concrete, let us start. Okay, the first thing we consider is the posterior density of lambda. Okay, and as I say, I will pay attention to this summation of quadratic terms, the star that I defined in the previous slide. And as I say, I will do computing square. And also, keep in mind our purpose is to calculate the posterior density of lambda. Okay, so the first thing I want to do is I want to collect all the terms with lambda, and then I will put all the terms without lambda behind it. Okay, and take a look at the third line here with the red parenthesis. I collect all the terms with lambda to here. And one note here is that remember, when we calculate the marginal density, I will take integration over lambda. So this term will be integrated. So the last two terms will be some important term when we are calculating the marginal density. And then let's continue the calculation. And the next two lines are some algebraic manipulation. My main purpose is, as I say, I need to collect all the terms with lambda, right? And at the same time, I want to do enough algebraic transformation so that it is of the form like this. Look at the second last line here. Lambda square minus 2 times lambda and some terms. Okay? Why? Because if it is of this form, then I can compute the square by doing what? By add and subtract the square of this term. My cursor is pointing this term. Okay, so this is what I do in the last line. In the last line here, I highlight the algebraic manipulation in red color. Okay, so essentially what I do here is I add and subtract the square of this term inside the parentheses, okay, so that I can complete the square, okay. So that's why I have a lambda minus a weighted sum of x and mu g square here. And I add the square of this term so that I can complete the square. So I have to minus the corresponding term so that to make the equality whole. So so that I have this term here minus some constant and then the square of a weighted sum of x and mu g. Okay. One note here is I put a orange parenthesis here and try to denote this term by double star. This is the term that I will consider later when we are calculating marginal distribution. But now let's pay attention to this quadratic term first. These are all the terms have lambda. So in fact, we don't need to explicitly calculate the functional form of the posterior density, and then we will know that what will be the mean and variance in the posterior density. And to be precise, by observing this term, we know that the mean in the posterior density is equal to this weighted sum of x and mu g, okay? And also the constant here, the term here, will be the inverse of the variance, And this conclusion is written in the next slide. Okay, here is the conclusion. The posterior density of lambda will be a normal density, and the mean will be, as I say, will be the weighted sum of x and mu g, and the weighting will be divided by their variance. And here are two more lines of algebraic manipulation, but they are different representation of the same term. And lastly, the last line is the variance in this posterior density, okay, just like what I say in last slide. Then let's try to consider the marginal density of X. We consider the term double star, which will be the last three terms in the previous calculation. Let me go back to refresh your memory. In orange parentheses, these three terms, I'm considering these three terms. And why I can ignore the terms with lambda, because I will take integration over lambda when we are calculating marginal density. So here I copy this three term in here, and as before, we will do computing square, right? And also we are considering the marginal density of X, so I need to collect all the term with X, okay, and see what will it look like so that we can determine the mean and variance. And here are the algebraic manipulation that I do. And first line, I highlight the manipulation in red. Essentially, I just want to simplify the term, and then I break the parentheses, two lines of algebra, and then I collect all the term with X here, and you will see there are 1, 2, 3. There are three terms of X here, right? Then we can further simplify. The last line are some further algebraic simplification. And then one more line of algebraic manipulation. It is of some very simple form so that we can use the computing square technique. And here the form is very simple, x squared minus 2x mu g. Okay, then we can compute the square by doing what? By add and subtract mu g squared inside the parentheses, right? The parentheses here, my cursor is pointing this term, right? Add and subtract mu squared. And then after add and subtract square, we get the last line. We compute the square, but we have one additional negative terms here, one additional negative term here. And it is interesting to notice that all these terms without x add up together exactly equal to 0. Okay, so it is very easy to observe that in the marginal density of x, the mean is mu g, and the variance is exactly the inverse of this constant, which is equal to sigma square plus sigma g square. Okay, and this conclusion is written here. The marginal density of x is a normal density. The expected value is mu g, and the variance is sigma square plus sigma g square. Now we can consider the decision. We considering, let me remind you that we are considering point estimation. The decision is a point estimate of lambda. Now we get this conclusion before, right? The decision is the posterior mean of lambda conditional on x, and also Bayes width. The Bayes width definition is written here in particular because we are considering point estimation. So the loss function here is the quadratic distance between decision and parameter. So everything are explicitly written down here. And then we can substitute the decision inside, and I try to highlight the inner integral. Okay, the inner integral is an integral over the parameter value lambda, and it is easy to observe that this is exactly the conditional variant of lambda, right? So we have the Bayes width equal to the conditional variant of lambda integrated over x. And we know that the conditional variant of lambda is equal to 1 over sigma square plus 1 over sigma g square inverse, right? So, and also it is independent of x. So when we integrate it, because f is a density, it is integrated to be 1. So lastly, the Bayes width is just equal to the conditional variant of lambda.